Right now, as you read these words, approximately 200 trillion particles of dark matter are passing through your body every single second. They're streaming through your skull, your heart, your hands, moving at speeds of hundreds of kilometers per second. They don't interact with the atoms that make up your flesh. They don't collide with your cells. They simply pass through you like you're not even there. And yet, without these invisible particles, you wouldn't exist. Your body, your planet, your solar system, the very galaxy you call home, none of it would have formed. The universe would be nothing but a thin, cold fog of hydrogen and helium, expanding forever into darkness, utterly incapable of creating anything as complex as a single living cell. This isn't speculation. This isn't philosophy. This is the conclusion of decades of astronomical observation, particle physics experiments, and cosmological modeling. Dark matter makes up approximately 85% of all matter in the universe. Everything you can see, every star, every planet, every galaxy, every human being who has ever lived, represents less than 15% of the matter that exists. We are the minority. We are the exception. And we owe our existence entirely to the invisible majority that surrounds us. The story of how scientists discovered this hidden universe is one of the most remarkable detective stories in the history of science. It begins not with a telescope pointed at distant galaxies, but with a simple question that refused to go away. Why don't galaxies fly apart? In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies located approximately 320 million light-years from Earth. Zwicky was measuring how fast individual galaxies were moving within this cluster, using a technique called spectroscopy that reveals the velocity of distant objects through shifts in their light. What he found made no sense. The galaxies were moving far too fast. According to Newton's laws of gravity, which had been tested and verified for centuries, galaxies moving at these speeds should have been flung out of the cluster long ago, scattered across the cosmos like sparks from a fire. Yet the Coma Cluster remained intact, held together by some invisible force. Zwicky performed the calculations again and again. He measured the visible mass of all the galaxies in the cluster, their stars, their gas clouds, everything that emitted or absorbed light. Then, he calculated how much mass would be needed to generate enough gravitational force to hold the cluster together at the observed speeds. The answer was staggering. The cluster needed approximately 400 times more mass than he could see. 400 times. Either Newton's laws were catastrophically wrong, or the universe was filled with matter that didn't emit light. Zwicky called this invisible substance, quote, zero, dark matter. His colleagues largely ignored him. For decades, his discovery gathered dust in academic journals, dismissed as an anomaly or a measurement error. But the evidence kept accumulating. In the 1970s, an American astronomer named Vera Rubin was studying the rotation curves of spiral galaxies. She focused her attention on Andromeda, our nearest large galactic neighbor, located approximately 2.5 million light-years away. Rubin measured how fast stars were orbiting around the galactic center at various distances. According to the laws of gravity, stars farther from the center should orbit more slowly, just as Neptune orbits the Sun more slowly than Earth does. The mathematics was straightforward. The predictions were clear. The observations shattered those predictions completely. Rubin discovered that stars at the outer edges of Andromeda were moving just as fast as stars closer to the center. Some were even moving faster. This should have been impossible. The only explanation was that galaxies were embedded in enormous halos of invisible matter, dark matter, that extended far beyond the visible disk of stars. This dark matter halo contained several times more mass than all the visible stars combined. It was the gravitational anchor that held the galaxy together, preventing it from tearing itself apart as it rotated. Rubin studied galaxy after galaxy, dozens, then hundreds. Every single one showed the same pattern. Every spiral galaxy in the universe was rotating too fast to be held together by its visible matter alone. The evidence was overwhelming. The universe was dominated by something we couldn't see. Now imagine you could rewind time. Not just a few years or centuries, but billions of years, back to the very beginning of the universe. 13.8 billion years ago, in the first moments after the Big Bang, the universe was a seething plasma of fundamental particles, far too hot for atoms to form. Matter and energy were mixed together in a state of almost perfect uniformity. Almost. There were tiny fluctuations in density, quantum ripples imprinted during the first fraction of a second of cosmic time. These ripples were incredibly small, variations of only 1 part in 100,000. But they were enough. As the universe expanded and cooled, these tiny density fluctuations began to grow. Regions that were slightly denser than average had slightly stronger gravity. They began to pull in surrounding matter. But here's the critical point. Normal matter, the protons, neutrons, and electrons that would eventually form atoms, couldn't collapse efficiently. It was still too hot. Photons, particles of light, were constantly colliding with the charged particles, creating radiation pressure that resisted gravitational collapse. Normal matter was locked in a cosmic tug-of-war between gravity trying to pull it together and radiation pressure pushing it apart. Dark matter faced no such obstacle. Because dark matter doesn't interact with light, it felt no radiation pressure. It responded only to gravity. While normal matter was still trapped in the cosmic plasma, unable to collapse, dark matter was already falling into the gravitational wells created by those primordial density fluctuations. It was building structure. It was creating the scaffolding upon which the visible universe would eventually form. By the time the universe was approximately 380,000 years old, it had cooled enough for the first atoms to form, a moment cosmologists call recombination. Suddenly, photons could travel freely through space. The universe became transparent, and normal matter, finally freed from radiation pressure, began to fall into the gravitational wells that dark matter had already carved out. Hydrogen and helium gas flowed along invisible filaments of dark matter, collecting in the densest regions, forming the first clouds that would eventually ignite as the first stars. Without dark matter, this process would never have happened. The density fluctuations in normal matter alone were too small. Gravity was too weak. Radiation pressure was too strong. The universe would have expanded forever as a nearly uniform fog of gas, growing thinner and colder with each passing eon. No galaxies would have formed, no stars would have ignited, no planets would have coalesced, no chemistry would have occurred, no life would have emerged. The universe would be dark, empty, and utterly sterile. But dark matter changed everything. Its gravitational influence amplified those tiny primordial fluctuations, turning quantum whispers into cosmic structures. Think of dark matter as the invisible framework of the universe, like the steel skeleton of a skyscraper. You don't see the steel beams when you look at a finished building. You see the glass, the concrete, the visible surfaces. But without that hidden framework, the building would collapse. Dark matter is the framework. Galaxies are the buildings. And we live inside one of those buildings, completely dependent on the invisible architecture that holds it all together. The Milky Way galaxy, our cosmic home, is embedded in a dark matter halo that extends approximately 600,000 light-years from the galactic center, roughly 6 times farther than the visible disk of stars. This halo contains approximately 1 trillion solar masses of dark matter. That's 1 trillion times the mass of our Sun, all in the form of particles we cannot see, cannot touch, cannot detect directly. And yet, this invisible halo is what keeps our galaxy intact. It's what prevents the stars in our galactic neighborhood from flying off into intergalactic space. It's what maintains the orbital stability that allows solar systems like ours to exist for billions of years without disruption. Our solar system orbits the galactic center at a speed of approximately 220 kilometers per second. At this velocity, we complete one full orbit around the galaxy every 225 million years, a period sometimes called a cosmic year. Earth has completed approximately 20 cosmic years since it formed 4.5 billion years ago. During each of these orbits, we're held in place not primarily by the gravity of the stars we can see, but by the gravity of the dark matter halo we cannot see. We are swimming through an ocean of invisible matter, and that ocean is what keeps us from drifting away into the void. But what exactly is dark matter? What are these particles that pass through your body by the trillions every second? The honest answer is, we don't know. Not yet. We know what dark matter does. We can measure its gravitational effects with extraordinary precision. We can map its distribution across the universe. We can simulate how it behaves over cosmic time. But we don't know what it's made of. We don't know what fundamental particles comprise this invisible substance that dominates the mass of the universe. The leading candidate is something called a WIMP, a weakly interacting massive particle. These hypothetical particles would have mass, which means they would interact gravitationally with normal matter. But they would interact only very weakly, if at all, through the other fundamental forces of nature. They wouldn't feel the electromagnetic force, which means they wouldn't emit, absorb, or reflect light. They would pass through normal matter almost as if it weren't there. Almost. There's a tiny chance that a dark matter particle might collide with an atomic nucleus. And that tiny chance is what scientists are desperately trying to detect. Deep underground, shielded from cosmic rays by kilometers of rock, physicists have built some of the most sensitive detectors ever created. The Xenon experiment, located beneath the Gran Sasso Mountain in Italy, uses approximately 3.5 metric tons of ultra-pure liquid xenon, cooled to -95 degrees Celsius. The detector is designed to catch the faint flash of light that would occur if a dark matter particle collided with a xenon nucleus. The experiment is so sensitive that it can detect events releasing energy equivalent to a single grain of sand dropping 1 millimeter. And yet, after years of operation, the detector has seen nothing definitive. If dark matter particles are passing through the detector, and they should be by the trillions, they're interacting even more weakly than predicted. Other experiments are trying different approaches. The Large Hadron Collider, the world's most powerful particle accelerator, is attempting to create dark matter particles by smashing protons together at energies approaching those present in the early universe. The idea is that if dark matter particles exist, they might be produced in these high-energy collisions. Scientists would then detect them indirectly by noticing that some energy and momentum seem to disappear, carried away by invisible particles that escape the detector. So far, no conclusive evidence has emerged. There are alternative theories. Some physicists propose that dark matter isn't made of particles at all, but consists of primordial black holes, tiny black holes formed in the first moments after the Big Bang, each perhaps no larger than a proton, but containing the mass of a mountain. Others suggest that we don't need dark matter at all, that our understanding of gravity itself is incomplete, and that a modified theory of gravity could explain the observations without invoking invisible matter. These alternatives are taken seriously and investigated rigorously. But so far, none of them explain the full range of observations as elegantly as dark matter does. The evidence for dark matter comes from multiple, independent lines of observation, and they all point to the same conclusion. There's the rotation of galaxies, which Vera Rubin documented. There's the motion of galaxies within clusters, which Fritz Zwicky first noticed. There's gravitational lensing, the bending of light around massive objects, which reveals the presence of mass even when no visible matter is present. Astronomers have observed cases where the gravitational lensing signal is offset from the visible galaxies, showing directly that the mass and the light are in different locations. The mass is where the dark matter is. The light is where the normal matter is. They don't always coincide. Perhaps the most dramatic evidence comes from a cosmic collision called the Bullet Cluster. Approximately 3.8 billion light-years from Earth, two galaxy clusters collided at speeds of several thousand kilometers per second. When the clusters smashed together, the hot gas that filled the space between galaxies, normal matter, collided and slowed down, creating a shock wave visible in X-ray observations. But the dark matter, which doesn't interact with normal matter except through gravity, passed right through. Gravitational lensing observations show that most of the mass in the system is not where the visible gas is, but where the galaxies are, carried along by the dark matter halos that surround them. The collision separated the dark matter from the normal matter, providing direct visual evidence that dark matter exists as a distinct substance. Every observation, every experiment, every simulation points to the same reality. We live in a universe dominated by something we cannot see. And this invisible substance isn't just a passive backdrop. It's the reason structure exists at all. It's the reason galaxies formed. It's the reason stars ignited. It's the reason planets coalesced. It's the reason chemistry became complex enough to produce life. Dark matter is the hidden architect of everything we see. Consider the cosmic web, the large-scale structure of the universe. If you could zoom out far enough to see billions of light-years in every direction, you would see that galaxies aren't distributed randomly. They're arranged in an intricate network of filaments and sheets, surrounding vast, empty voids. This cosmic web looks remarkably like a neural network, with dense nodes connected by long filaments, separated by empty spaces. The resemblance isn't coincidental. Both structures are shaped by similar mathematical principles. The way matter flows along gravitational gradients, clustering in some regions while evacuating others. But the cosmic web we see, the galaxies and galaxy clusters, is just the visible tip of a much larger structure. The filaments are made primarily of dark matter. Galaxies form where these dark matter filaments intersect, where the density is highest. The Milky Way sits at the intersection of several dark matter filaments, part of what astronomers call the local group, which also includes Andromeda and several dozen smaller galaxies. We're all embedded in the same dark matter structure, all held together by the same invisible web. This web extends across the entire observable universe. It contains approximately 2 trillion galaxies, each embedded in its own dark matter halo, each connected to its neighbors through dark matter filaments. The total mass of dark matter in the observable universe is approximately 6 times 10 to the power of 53 kilograms. That's a 6, followed by 53 zeros. Written out in words, 600 quintillion 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 kilograms. And that's just the dark matter. The total mass energy of the universe, including dark energy, is even larger. You are part of this structure. Not metaphorically, literally. The atoms in your body were forged in stars that formed within dark matter halos. Those stars exploded as supernovae, scattering heavy elements across space. Those elements collected in new clouds of gas, still guided by dark matter's gravity, and formed new stars and planets. One of those planets was Earth. The calcium in your bones, the iron in your blood, the carbon in your DNA. All of it was assembled in a process that depended entirely on dark matter's gravitational scaffolding. And right now, you're moving through the Milky Way's dark matter halo at 220 kilometers per second. You're orbiting the galactic center, along with the Sun and all the other stars in our neighborhood. You're embedded in a structure that extends hundreds of thousands of light-years in every direction. You're part of a cosmic web that spans billions of light-years. You're connected, through gravity, to every galaxy in the observable universe. The dark matter particles passing through your body right now have been traveling for billions of years. Some of them may have passed through the primordial gas clouds that formed the first stars. Some may have witnessed the birth of galaxies. Some may have been present when the solar system formed 4.5 billion years ago. They carry no information about these events. They interact too weakly to record anything. But they were there. They've been part of the universe's story since the beginning. And they're still here, still shaping the cosmos, still holding everything together. Without them, galaxies would dissolve, stars would drift apart, planetary systems would become unstable, the universe would unravel. But with them, structure persists, complexity grows, life emerges, consciousness arises. And that consciousness can look out at the universe and ask, what holds all this together? What invisible force prevents the cosmos from flying apart? The answer is all around you. It's passing through you right now. It's the dark matter halo that cradles our galaxy, the cosmic web that connects all galaxies, the invisible architecture that makes existence possible. The dark matter halo surrounding our galaxy isn't uniform. It isn't a smooth sphere of invisible particles distributed evenly through space. It's structured, dynamic, shaped by billions of years of cosmic evolution. And understanding this structure, mapping the invisible architecture that holds our galaxy together, has become one of the most ambitious projects in modern astronomy. Picture the Milky Way as you've seen it in photographs, a luminous spiral disk, approximately 100,000 light-years across, with graceful arms of stars and gas spiraling outward from a bright central bulge. This is what we see. But what we see is misleading. The visible disk is embedded within a dark matter halo that extends at least 6 times farther, creating a roughly spherical structure approximately 600,000 light-years in diameter. If you could see dark matter, the Milky Way wouldn't look like a flat spiral at all. It would look like a vast, diffuse sphere with a thin, bright disk embedded in its center, like a fried egg, with the yolk representing the visible galaxy and the white representing the dark matter halo. But even this image is too simple. The dark matter halo isn't perfectly spherical. It's slightly flattened, compressed along the axis perpendicular to the galactic disk. Computer simulations suggest it's also lumpy, filled with substructures, smaller clumps of dark matter that survived from earlier stages of galaxy formation. These substructures are the remnants of smaller dark matter halos that merged together over billions of years to form the Milky Way's current halo. Some of these clumps may contain as much mass as 10 million suns, yet they're completely invisible, detectable only through their gravitational influence on nearby stars. Astronomers have found evidence for these substructures by studying stellar streams, long ribbons of stars that stretch across the sky, the remnants of small galaxies and star clusters that were torn apart by the Milky Way's gravity. The Sagittarius Stream, for example, wraps completely around our galaxy, a trail of stars pulled from the Sagittarius dwarf galaxy as it orbits through the Milky Way's halo. By measuring the positions and velocities of stars in these streams with extraordinary precision, astronomers can detect tiny gravitational perturbations, subtle tugs that reveal the presence of dark matter clumps passing nearby. It's like watching ripples on a pond and deducing the presence of invisible fish swimming beneath the surface. The European Space Agency's Gaia mission has revolutionized this field. Launched in 2013, Gaia has measured the positions and motions of nearly 2 billion stars with unprecedented accuracy. Precise enough to measure the width of a human hair from a distance of 1,000 kilometers. This data has revealed structures in the Milky Way that were completely unknown before. Streams of stars, shells of stars, ripples in the stellar disk. Each of these features tells a story about the galaxy's history, about past collisions and mergers, about the distribution of dark matter that shaped these events. One of the most remarkable discoveries came from analyzing the motion of stars in the solar neighborhood, the region within a few hundred light-years of the Sun. Astronomers found that stars aren't moving randomly. They're organized into groups with similar velocities, moving together through space like schools of fish. Some of these groups are the remnants of star clusters that form together and are slowly drifting apart. But others appear to be stars that were disturbed by the same gravitational event, perhaps the passage of a dark matter substructure through the galactic disk, or the gravitational wake of a dwarf galaxy that plunged through the Milky Way millions of years ago. These observations are teaching us that the Milky Way isn't a static, unchanging structure. It's dynamic, constantly evolving, shaped by ongoing interactions with dark matter and with smaller galaxies that venture too close. Right now, the Sagittarius dwarf galaxy is being torn apart by the Milky Way's gravity, its stars stripped away and scattered into streams. The Large and Small Magellanic Clouds, two small galaxies visible from the southern hemisphere, are also being gravitationally disrupted, leaving behind a stream of gas and stars called the Magellanic Stream that stretches across more than 100 degrees of the sky. These interactions are stirring the dark matter halo, creating waves and ripples that propagate through the invisible structure surrounding our galaxy. And we're part of this motion. The Sun, along with all the planets and everything in the solar system, is moving through the dark matter halo at approximately 220 kilometers per second. But this motion isn't smooth. As we orbit the galactic center, we also bob up and down through the galactic disk, crossing through the midplane approximately every 30 million years. This oscillation takes us through regions of varying dark matter density. When we're in the midplane, we're passing through the densest part of the disk, where dark matter is concentrated along with visible matter. When we're above or below the plane, we're moving through the more diffuse regions of the halo. Some scientists have speculated that this oscillation might have consequences for life on Earth. As the solar system passes through the galactic midplane, it encounters not just dark matter, but also giant molecular clouds, vast regions of dense gas where new stars are forming. The gravitational influence of these clouds could disturb the Oort cloud, a spherical shell of icy bodies surrounding the solar system at a distance of approximately 1 light-year. This disturbance could send comets plunging toward the inner solar system, increasing the rate of impacts on Earth. Some researchers have proposed that mass extinction events in Earth's history might correlate with the solar system's passages through the galactic midplane, though this hypothesis remains controversial and unproven. What's certain is that we're not isolated from the galaxy around us. We're embedded in it, influenced by it, shaped by forces that operate on scales vastly larger than our solar system. The dark matter halo that surrounds us isn't just a passive backdrop, it's an active participant in the galaxy's evolution, and by extension, in our own history. Now consider what happens when you try to detect this invisible ocean directly. The challenge is staggering. Dark matter particles, if they're WIMPs, as many physicists suspect, interact so weakly with normal matter that a single particle might pass through the entire Earth without colliding with a single atom. To have any hope of detecting them, you need to create an environment where even the rarest interactions can be observed. This is why dark matter detectors are built deep underground. The Sanford Underground Research Facility in South Dakota, for example, is located nearly 1.5 kilometers beneath the surface, in a former gold mine. At this depth, the rock overhead shields the detectors from cosmic rays, high-energy particles from space that constantly bombard Earth's surface. Cosmic rays would create so much background noise that any signal from dark matter would be completely drowned out. But 1.5 kilometers of rock stops nearly all cosmic rays, creating an environment quiet enough that the faint whisper of a dark matter interaction might be heard. The Lux-Zeppelin experiment, currently operating at this facility, uses 10 metric tons of liquid xenon as a target. The xenon is purified to extraordinary levels, less than 1 part per trillion of radioactive contaminants, because even tiny amounts of radioactivity would create background signals that could be mistaken for dark matter. The detector is surrounded by layers of shielding, water tanks to block neutrons, lead bricks to block gamma rays, copper plates to absorb X-rays. Every material is carefully selected for its low radioactivity. Every component is tested and retested. The goal is to create the quietest environment possible, a place where the universe's faintest signals might be detected. When a particle interacts with a xenon nucleus, it creates a tiny flash of light and a small pulse of ionization, electrons knocked free from atoms. The detector captures both signals, using arrays of sensitive photomultiplier tubes that can detect individual photons. By comparing the light signal and the ionization signal, scientists can determine what kind of particle caused the interaction. Different particles create different ratios of light to ionization. A dark matter particle, if it interacts at all, should create a very specific signature, a low-energy nuclear recoil with a particular ratio of light to charge. The experiment has been running for years. It has recorded millions of events, and in all that data, there's no clear signal of dark matter. There are events that look interesting, events that could potentially be dark matter interactions, but none that rise above the background with enough statistical significance to claim a discovery. The universe is being stubbornly silent. This silence is itself informative. It tells us that if dark matter is made of WIMPs, those particles interact even more weakly than many theoretical models predicted. It's pushing physicists to consider alternative possibilities. Maybe dark matter particles are much lighter than expected, too light to create detectable nuclear recoils. Maybe they're much heavier, so rare that we simply haven't seen one yet. Maybe they interact through forces we haven't discovered yet, forces that don't couple to the particles in our detectors. Or maybe dark matter isn't made of particles at all. Some physicists are exploring the possibility that dark matter consists of axions, hypothetical particles that are incredibly light, perhaps a trillion times lighter than an electron. Axions wouldn't create nuclear recoils. Instead, they would interact with electromagnetic fields in subtle ways. Experiments like ADMX, the Axion Dark Matter Experiment, are searching for these interactions using powerful magnetic fields and ultra-sensitive microwave detectors. The idea is that axions passing through a strong magnetic field might convert into photons, particles of light, at a very specific frequency determined by the axion's mass. By tuning the detector to different frequencies, like tuning a radio, scientists are searching for the faint signal of axions converting into photons. So far, ADMX has searched a range of possible axion masses and found nothing. But the range of possible masses is enormous, spanning more than 20 orders of magnitude, and the experiment has only explored a tiny fraction of that space. The search continues, frequency by frequency, year by year, looking for a signal that might not exist, or might be just beyond the current sensitivity of the detector. There's also the possibility that dark matter is something even stranger. Some theories propose that dark matter particles can interact with each other, even if they don't interact with normal matter. These self-interacting dark matter models predict that dark matter halos should have different structures than standard models predict, perhaps with flatter cores instead of dense centers. Observations of dwarf galaxies, small galaxies that are dominated by dark matter, have found some evidence for these flatter cores, though the data is still ambiguous and hotly debated. Other theories suggest that dark matter might be made of primordial black holes formed in the first fraction of a second after the Big Bang, before the first stars existed. These black holes could have a wide range of masses, from less than the mass of a mountain to thousands of times the mass of the Sun. If dark matter is made of primordial black holes, we wouldn't detect them with particle detectors. Instead, we detect them through gravitational effects, the way they bend light, the way they disturb the orbits of stars, the gravitational waves they produce when they collide. Recent observations have added intriguing hints to this possibility. The LIGO and Virgo gravitational wave detectors have observed dozens of black hole mergers, and some of these black holes have masses that are difficult to explain through normal stellar evolution. Could some of them be primordial black holes? Could dark matter be hiding in plain sight, not as exotic particles, but as the most extreme objects predicted by Einstein's theory of gravity? The evidence is far from conclusive, but the possibility is being taken seriously. What's remarkable is that despite decades of searching, despite experiments of extraordinary sensitivity, despite theoretical models of great sophistication, we still don't know what dark matter is. We can map its distribution across the universe. We can measure its gravitational effects with exquisite precision. We can simulate how it behaves over billions of years of cosmic evolution. But we cannot capture it. We cannot isolate it. We cannot examine it directly. This might seem frustrating, even embarrassing. How can we claim to understand the universe when we don't know what 85% of its matter is made of? But there's another way to look at it. The fact that we've discovered dark matter at all That we've deduced the existence of an invisible substance purely through its gravitational effects is a testament to the power of scientific reasoning. We've never seen dark matter. We've never touched it. We've never detected a single particle of it with certainty. And yet we know it's there. We know how much of it there is, and we know what role it plays in cosmic structure formation. We've mapped the invisible. Consider the parallels with other great discoveries in physics. When Neptune was discovered in 1846, it wasn't found by pointing a telescope at a random patch of sky. It was found by calculating where an unseen planet must be, based on irregularities in the orbit of Uranus. Astronomers predicted Neptune's existence and location through mathematics before they ever saw it through a telescope. Dark matter is similar, but on a vastly larger scale. We've predicted its existence, mapped its distribution, and understood its role in cosmic evolution, all without directly detecting it. The same is true for many fundamental aspects of reality. We've never seen an atom directly, yet we know atoms exist, and we understand their structure in extraordinary detail. We've never seen the inside of the sun, yet we know it's powered by nuclear fusion, and we can calculate the temperature and pressure at its core. We've never traveled to the center of the Earth, yet we know it contains a solid iron core surrounded by a liquid outer core, deduced from the way seismic waves propagate through the planet. Science is fundamentally about inference, about building models that explain observations, about deducing the invisible from the visible. Dark matter is perhaps the ultimate example of this process. It's a substance that reveals itself only through gravity, the weakest of the fundamental forces, acting over cosmic distances and timescales. And yet, through careful observation and rigorous analysis, we've learned that this invisible substance is the dominant form of matter in the universe, the scaffolding upon which all visible structure is built. The search for dark matter's true nature continues in laboratories around the world. New detectors are being built, more sensitive than ever before. New theoretical models are being developed, exploring possibilities that seemed too exotic to consider just a few years ago. New astronomical surveys are mapping the distribution of dark matter with unprecedented precision, looking for clues in the way it shapes galaxies and galaxy clusters. The mystery remains unsolved, but the investigation is far from over. And while we search, the dark matter continues its work. It holds galaxies together. It guides the formation of new structures. It shapes the cosmic web that spans the universe. It passes through your body, through the Earth, through the sun, utterly indifferent to the normal matter it encounters, responding only to the pull of gravity. Right now, as you exist in this moment, you're part of a structure that extends across hundreds of thousands of light years. The dark matter halo that surrounds the Milky Way is holding you in orbit around the galactic center, maintaining the stability that allows stars and planets to exist for billions of years. You're embedded in this invisible architecture, dependent on it, shaped by it, connected through it to every other galaxy in the universe. The atoms in your body, the carbon, the oxygen, the nitrogen, the calcium, the iron, were all forged in stars that formed within dark matter halos. Those stars lived and died within the gravitational embrace of dark matter. When they exploded as supernovae, scattering their enriched material across space, that material was guided by dark matter's gravity into new clouds, new stars, new planets. The Earth itself formed from material that had been shepherded by dark matter for billions of years, cycling through generations of stars, accumulating the heavy elements necessary for rocky planets, and eventually, for life. Every breath you take contains oxygen atoms that were created in massive stars, stars that could only form because dark matter provided the gravitational framework. Every heartbeat is powered by chemical reactions involving elements that were synthesized in stellar cores, cores that ignited because dark matter allowed gas clouds to collapse. Every thought you think involves electrical signals propagating through neurons, neurons built from molecules, molecules built from atoms, atoms that exist because dark matter made the universe capable of creating structure. You are not separate from the cosmos. You are not an isolated observer looking at the universe from the outside. You are part of it, woven into its fabric. your existence dependent on processes that operate on scales from the subatomic to the cosmic. The dark matter that holds galaxies together is the same dark matter that made your existence possible. The invisible architecture that spans the universe is the foundation upon which your life is built. And this architecture is still evolving. The universe is not static. Galaxies are still forming, still merging, still being shaped by dark matter's gravity. The Milky Way is on a collision course with Andromeda, our nearest large galactic neighbor. In approximately 4 billion years, the two galaxies will begin to merge, their dark matter halos interpenetrating, their stars and gas clouds interacting, their supermassive black holes eventually spiraling together. The collision will reshape both galaxies, creating a new, larger elliptical galaxy that astronomers have already nicknamed Milkomeda. This merger is inevitable, written into the trajectories of the two galaxies by the distribution of dark matter in the local group. The dark matter halos of the Milky Way and Andromeda are already interacting gravitationally, pulling the galaxies together at a speed of approximately 110 kilometers per second. Nothing can stop this collision. It's part of the ongoing process of structure formation, the same process that built galaxies in the first place, now operating on larger scales as galaxies merge to form galaxy groups and clusters. When the merger happens, the solar system will likely survive intact. The distances between stars are so vast that direct collisions are extremely unlikely. But the Sun's orbit around the galactic center will change dramatically. We might be flung into the outer regions of the new galaxy, or we might be pulled closer to the center. The night sky will be transformed. Andromeda, currently a faint smudge visible to the naked eye, will grow larger and brighter as it approaches, eventually filling a significant portion of the sky. The merger will trigger bursts of star formation as gas clouds collide and compress. New stars will ignite. New planetary systems will form. The universe will continue its work of creating structure, building complexity, generating the conditions for new possibilities to emerge. All of this is orchestrated by dark matter. The merger of the Milky Way and Andromeda is happening because their dark matter halos are gravitationally bound, pulling the galaxies together despite the expansion of the universe. The new galaxy that forms will have a dark matter halo containing the combined mass of both original halos, approximately 2 trillion solar masses of invisible matter, extending more than 1 million light-years from the center. This new halo will be the gravitational anchor for the merged galaxy, holding it together, shaping its evolution, providing the framework for future generations of stars and planets. And throughout this process, dark matter particles will continue passing through everything, unaffected by the cosmic drama unfolding around them. They'll pass through the gas clouds where new stars are forming. They'll pass through the stars themselves. They'll pass through any planets that exist, any life that might have emerged on those planets, any consciousness that might be observing the merger and wondering about its place in the cosmos. Dark matter is the silent partner in every cosmic event, the invisible force that makes everything possible while remaining forever in the background, undetected and undetectable by any means except gravity. This is the paradox of dark matter. It's the most abundant form of matter in the universe, yet we cannot see it. It's the foundation of all cosmic structure, yet we don't know what it's made of. It's passing through us constantly, yet we cannot feel it. It shaped our existence, yet it remains profoundly alien, fundamentally different from the matter we're made of, interacting with our world only through the weakest of forces. But perhaps this is appropriate. Perhaps the universe is telling us something profound about the nature of reality. We are made of atoms, protons, neutrons, electrons, particles that interact through all 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These interactions make us visible, tangible, capable of complex chemistry and biology. But we are the exception. Most of the matter in the universe doesn't interact through these forces. It responds only to gravity. It's invisible, intangible, incapable of forming atoms or molecules, or anything resembling the structures we're familiar with. We live in a universe where the majority of matter is fundamentally different from us, where the visible is the minority and the invisible is the norm. This should be humbling. It should remind us that our perspective is limited, that the universe we see is not the whole universe, that reality extends far beyond what our senses can detect or our instruments can measure. We are embedded in a cosmos that is stranger and more mysterious than we ever imagined. A cosmos where the invisible outweighs the visible, where the unknown dwarfs the known. And yet, we continue to investigate. We build detectors deep underground, searching for the faintest signals. We launch telescopes into space, mapping the distribution of dark matter across billions of light years. We run simulations on supercomputers, modeling the evolution of dark matter halos over cosmic time. We develop new theories, exploring possibilities that challenge our understanding of physics. We refuse to accept ignorance as final. We insist on understanding, even when understanding seems impossibly difficult. This is what makes us human. Not our atoms, those are common throughout the universe. Not our chemistry, that's just physics and probability. What makes us human is our curiosity, our drive to understand, our refusal to accept mystery as permanent. We are the universe becoming aware of itself, asking questions about its own nature, seeking to understand the invisible forces that shaped its evolution. Dark matter is one of those forces. It's the invisible architect, the hidden framework, the silent partner in cosmic creation. It made galaxies possible. It made stars possible. It made planets possible. It made us possible. And now we, the products of this long cosmic process, are trying to understand the very substance that made our existence possible. The search continues. The mystery remains. But the investigation itself is part of the story, part of the ongoing process by which the universe comes to understand itself. We are dark matter's way of knowing that it exists. We are the cosmos investigating its own foundations. And in that investigation, in that search for understanding, we fulfill our role in the universe's grand narrative. The dark matter passes through you. You pass through the dark matter. And in that mutual interpenetration, in that cosmic dance of visible and invisible, the universe continues its work of creating structure, building complexity, generating consciousness, and asking questions about its own nature. To understand how profoundly dark matter shapes reality, we need to rewind time to an era when the universe was unrecognizable, a period so early that atoms didn't exist, when the cosmos was a seething ocean of particles and radiation, expanding and cooling from the initial moment of creation. 380,000 years after the Big Bang, the universe reached a critical threshold. For the first time, it became cool enough for electrons to bind with protons, forming the first hydrogen atoms. This moment, called recombination, transformed the cosmos. Before recombination, photons, particles of light, were constantly scattering off free electrons, making the universe opaque, like trying to see through fog. After recombination, photons could travel freely. The universe became transparent. The light released at that moment has been traveling through space ever since, stretched by cosmic expansion into microwave wavelengths. We call it the cosmic microwave background, or CMB, the oldest light in the universe, a baby picture of the cosmos taken when it was less than 1/400,000th of its current age. When astronomers first mapped the CMB in detail using satellites like COBE, WMAP, and Planck, they discovered something extraordinary. The temperature of this ancient light isn't perfectly uniform. There are tiny fluctuations, hot spots and cold spots, varying by only about 1 part in 100,000. These fluctuations are the imprints of density variations in the early universe, quantum ripples from the first fraction of a second after the Big Bang, amplified by cosmic inflation and preserved in the fabric of space itself. These tiny ripples are the seeds of everything that exists today. Every galaxy, every star, every planet, every atom in your body can trace its history back to these primordial density fluctuations. But here's the critical insight. The fluctuations in normal matter alone were too small to grow into galaxies. The universe was expanding too fast. Gravity was too weak. Without something else, without some additional gravitational pull, those tiny ripples would have remained tiny forever, smoothed out by the expansion of space. Dark matter changed everything. Because dark matter doesn't interact with photons, it began collapsing into gravitational wells long before normal matter could. While normal matter was still locked in a plasma state, buffeted by radiation pressure, dark matter was already building structure. It was creating gravitational potential wells, invisible valleys in the fabric of space-time, that would eventually trap normal matter once it cooled enough to respond. Computer simulations of this process reveal something breathtaking. When cosmologists model the evolution of the universe from the Big Bang to the present day, incorporating both normal matter and dark matter, they see structure emerge in a specific sequence. First, small dark matter halos form, clumps containing perhaps 1 million solar masses, appearing within the first few 100 million years after the Big Bang. These small halos merge together, building larger structures through a process called hierarchical assembly. Smaller halos combine to form bigger halos. Bigger halos merge to form even larger ones. Over billions of years, this process builds the cosmic web we see today, a vast network of filaments and nodes, with galaxy clusters at the intersections and vast voids in between. The Millennium Simulation, one of the most detailed cosmological simulations ever performed, tracked the evolution of more than 10 billion dark matter particles from the early universe to the present day. The simulation required months of computing time on some of the world's most powerful supercomputers. The results are stunning. The simulated universe looks remarkably like the real universe. The distribution of galaxies, the structure of galaxy clusters, the cosmic web of filaments, all of it matches observations with extraordinary precision. This isn't a coincidence. It's confirmation that our understanding of dark matter's role in structure formation is fundamentally correct. But the simulation reveals something else, something that challenges our intuition about how structure forms. In the early universe, dark matter halos formed everywhere, in vast numbers. Most of these halos were small, too small to trap enough normal matter to form stars. They remain dark to this day, invisible halos of dark matter drifting through intergalactic space, containing no stars, no gas, nothing that emits light. Astronomers call these dark galaxies, though that's a misnomer. They're not galaxies at all, just dark matter halos that never accumulated enough normal matter to become visible. The Milky Way itself is surrounded by hundreds, perhaps thousands, of these dark halos. They're the remnants of the hierarchical assembly process, small structures that were absorbed into the Milky Way's gravitational sphere of influence, but never merged completely. Some of them may be passing through the galactic disk right now, invisible rivers of dark matter flowing through the space between stars. Their gravitational influence is subtle but detectable. When one of these dark halos passes near a stellar stream, those ribbons of stars torn from disrupted dwarf galaxies, it creates a small gravitational perturbation, a tiny deviation in the stream's trajectory. By measuring these deviations with sufficient precision, astronomers can map the distribution of dark matter substructure within our galaxy. The Gaia satellite has made this possible. Its measurements of stellar positions and velocities are so precise that astronomers can detect perturbations caused by dark matter clumps containing as little as a few million solar masses. Several candidate detections have already been reported, gaps and wiggles in stellar streams that suggest the passage of invisible dark matter halos. Each detection is a glimpse of the hidden scaffolding that surrounds us, the invisible architecture that shaped our galaxy's formation and continues to influence its evolution. Now expand your perspective beyond our galaxy, beyond the local group, to the largest structures in the universe. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, are the most massive gravitationally bound structures that exist. The Coma cluster, which Fritz Zwicky studied in the 1930s, contains more than 1,000 galaxies, and has a total mass of approximately 10 to the power of 15 solar masses, 1 quadrillion times the mass of the Sun. But only about 2% of that mass is in the form of stars. Another 13% is hot gas filling the space between galaxies, so hot it emits X-rays. The remaining 85% is dark matter. This ratio, 85% dark matter, 15% normal matter, appears again and again throughout the universe. It's not just true for galaxy clusters, it's true for individual galaxies. It's true for the universe as a whole. Everywhere we look, dark matter dominates. This consistency is itself evidence that dark matter is real, that it's a fundamental component of cosmic structure, not an artifact of our measurements or a flaw in our understanding of gravity. The distribution of dark matter in galaxy clusters has been mapped using gravitational lensing, the bending of light by massive objects predicted by Einstein's general theory of relativity. When light from distant galaxies passes through a galaxy cluster, the cluster's gravity bends the light's path, distorting the images of background galaxies into arcs and rings. By measuring these distortions, astronomers can reconstruct the distribution of mass in the cluster, including the dark matter that produces most of the gravitational lensing. The results are remarkable. Dark matter in galaxy clusters forms smooth, extended halos centered on the cluster's core. The distribution follows a predictable pattern called the NFW profile, named after the three astrophysicists who first described it: Navarro, Frank, and White. This profile shows that dark matter density is highest at the center of the cluster and decreases gradually with distance, following a specific mathematical relationship. The fact that this same profile appears in clusters throughout the universe, regardless of their size or age, suggests that dark matter behaves according to simple, universal laws. Laws we can model and predict, even if we don't yet know what dark matter particles are. But gravitational lensing has revealed something even more profound. In some cases, the lensing signal, the distortion of background galaxies, is offset from the visible matter in the cluster. The most famous example is the Bullet cluster, which we mentioned earlier, but there are others. MACS J0025.4-1222, a cluster located approximately 2.7 billion light-years away, shows a similar separation between dark matter and normal matter. So does Able 520, sometimes called the _3_, because of its complex structure resulting from multiple galaxy collisions. These systems are cosmic laboratories. When galaxy clusters collide at speeds of thousands of kilometers per second, the hot gas between galaxies, normal matter, collides and slows down, creating shock waves visible in X-ray observations. But the dark matter, which interacts only through gravity, passes through with minimal interaction. The collision separates the dark matter from the normal matter, allowing astronomers to see them independently. The gravitational lensing maps show clearly that most of the mass is not where the hot gas is, but where the galaxies are, carried along by their dark matter halos. These observations rule out many alternative theories. If there were no dark matter, if the observations could be explained by modifying the laws of gravity instead, then the gravitational lensing signal should always coincide with the visible matter. But it doesn't. The separation between dark matter and normal matter in colliding clusters is direct visual evidence that dark matter exists as a distinct substance, not just a gravitational anomaly. The cosmic web, the large-scale structure of the universe, is perhaps the most dramatic manifestation of dark matter's influence. When astronomers map the positions of millions of galaxies across billions of light-years, they see a pattern that looks like a three-dimensional spiderweb. Galaxies are arranged along filaments, thin threads of matter stretching across hundreds of millions of light-years. Where filaments intersect, galaxy clusters form. Between the filaments are vast voids, regions containing very few galaxies, spanning hundreds of millions of light-years across. This structure isn't random. It's the inevitable result of how dark matter responds to gravity over cosmic time. The initial density fluctuations in the early universe, those tiny ripples in the CMB, had a specific pattern, a specific distribution of scales. As dark matter collapsed under its own gravity, it amplified these patterns, creating structure on multiple scales simultaneously. Small halos formed first, then merged into larger halos. Filaments formed where multiple halos were aligned. Voids formed where the initial density was slightly lower than average, evacuated as matter flowed toward denser regions. The Sloan Digital Sky Survey has mapped this structure in unprecedented detail, measuring the positions and distances of more than 3 million galaxies. When these galaxies are plotted in three-dimensional space, the cosmic web becomes visible. You can see the filaments. You can see the clusters. You can see the voids. And when cosmologists compare this observed structure to simulations of dark matter evolution, the match is extraordinary. The simulations predict the same filamentary structure, the same distribution of cluster sizes, the same abundance of voids. The agreement between theory and observation is so precise that it allows cosmologists to measure fundamental properties of the universe, its age, its expansion rate, its matter content, with remarkable accuracy. One of the most powerful techniques for studying the cosmic web is called baryon acoustic oscillations, or BAO. In the early universe, before recombination, sound waves propagated through the plasma of normal matter and radiation. These sound waves created a characteristic scale, a preferred distance of approximately 490 million light-years, imprinted in the distribution of matter. After recombination, when the universe became transparent, these sound waves stopped propagating, but the density pattern they created was frozen into the distribution of matter. As structure formed, this pattern was preserved. Today, galaxies are slightly more likely to be separated by this characteristic distance than by other distances. By measuring the distribution of galaxies across the sky and looking for this subtle excess at the BAO scale, astronomers can use the cosmic web as a cosmic ruler. The BAO scale is determined by the physics of the early universe, which we understand well. By measuring how large this scale appears in the sky at different distances, different cosmic epochs, astronomers can track the expansion history of the universe. This technique has confirmed that the universe's expansion is accelerating, driven by dark energy, and has measured the acceleration rate with precision. Dark energy is another mystery, distinct from dark matter but equally profound. While dark matter pulls things together through gravity, dark energy pushes things apart, causing the expansion of the universe to accelerate. Dark energy makes up approximately 68% of the total energy content of the universe. Dark matter makes up approximately 27%. Normal matter, everything we can see, everything we're made of, makes up only about 5%. We live in a universe where 95% of the total energy content is in forms we don't understand. But dark matter and dark energy play different roles. Dark matter is essential for structure formation. Without it, galaxies wouldn't exist. Dark energy, in contrast, works against structure formation. It's causing the universe to expand faster and faster, pulling galaxy clusters apart. Eventually, in the far future, it will overcome even the gravity holding galaxies together. The balance between dark matter and dark energy determines the fate of cosmic structure. In the early universe, dark matter dominated, allowing structure to form. In the future, dark energy will dominate, eventually tearing structure apart. We live in a special epoch, a brief window in cosmic history when both dark matter and dark energy are important, when structure has formed but hasn't yet been destroyed. This epoch won't last forever. In approximately 100 billion years, the accelerating expansion driven by dark energy will have carried distant galaxies so far away that their light can no longer reach us. The observable universe will shrink. Eventually, only the local group, the Milky Way, Andromeda, and a few dozen smaller galaxies, all bound together by dark matter's gravity, will remain visible. The rest of the universe will have receded beyond the cosmic horizon, carried away by expansion faster than light can travel. Astronomers in that distant future, if any exist, will look out at a universe that appears almost empty. They'll see their own galaxy, perhaps a few nearby companions, and nothing else. The cosmic microwave background will have been stretched to such long wavelengths that it will be undetectable. The evidence for the Big Bang, for cosmic expansion, for the existence of other galaxies, all of it will have vanished beyond the horizon. Those future astronomers will have no way to know that the universe was once filled with billions of galaxies, that it had a beginning, that it evolved from a hot, dense state. The evidence will be gone, erased by cosmic expansion. This raises a profound question. What evidence are we missing? What aspects of the universe's history or structure have already receded beyond our cosmic horizon, leaving no trace we can detect? We know the universe is 13.8 billion years old, but we can only see back to the moment of recombination, 380,000 years after the Big Bang. The earlier history, the first moments, the era of inflation, the origin of the density fluctuations that seeded all structure, is hidden from direct observation. We can infer what happened through theory and indirect evidence, but we cannot see it directly. Dark matter itself may be hiding evidence. If dark matter particles can interact with each other through forces we haven't discovered, they might form complex structures we can't detect. Some theories propose that dark matter could form, quote, 4, or even, quote, 5, bound together by a, quote, 6 that doesn't couple to normal matter. These structures would be completely invisible to us, detectable only through their collective gravitational influence. There could be an entire dark sector of physics, a shadow universe of particles and forces, coexisting with our own, but interacting only through gravity. This isn't science fiction. It's a serious theoretical possibility being explored by physicists. The Standard Model of Particle Physics, our best theory of fundamental particles and forces, contains only one type of matter, the quarks and leptons that make up normal atoms. But there's no fundamental reason why nature should be so simple. The universe could contain multiple types of matter, multiple sectors of particles, each with their own forces and interactions. We would only be aware of the sector we're part of, the sector that interacts electromagnetically and can form atoms and molecules and complex chemistry. The other sectors would be dark to us, invisible, detectable only through gravity. If this is true, then dark matter might not be a single type of particle, but a whole family of particles, as diverse and complex as the particles in the Standard Model. There might be dark photons, dark electrons, dark quarks. There might be dark stars, dark planets, even dark life, structures made of dark matter, held together by dark forces, existing in the same space as our own universe, but completely invisible to us. This seems fantastical, but it's consistent with everything we know. We have no evidence for such complexity in the dark sector, but we have no evidence against it either. Dark matter remains profoundly mysterious. What we do know is that dark matter is essential. Without it, the universe would be radically different, simpler, emptier, incapable of producing the complexity we see around us. The density fluctuations in the early universe would have remained tiny. Gravity would have been too weak to amplify them. The universe would have expanded as a nearly uniform fog of hydrogen and helium, growing thinner and colder with each passing eon. No galaxies would have formed, no stars would have ignited, no heavy elements would have been synthesized, no planets would have coalesced. No chemistry would have become complex enough to produce life. Dark matter made structure possible. It provided the gravitational scaffolding that allowed normal matter to collapse and form galaxies. It created the cosmic web that spans the universe. It enabled the formation of stars and planets. It made the universe interesting, complex, capable of producing observers who could look out and wonder about their origins. And this scaffolding is still active, still shaping the cosmos. Right now, dark matter is guiding the formation of new galaxies in the distant universe. It's steering the merger of the Milky Way and Andromeda. It's holding galaxy clusters together against the pull of dark energy. It's maintaining the stability of the cosmic web, preserving structure even as the universe expands. Dark matter is the invisible hand that shapes cosmic evolution, the hidden force that makes the universe what it is. Consider the scale of this influence. The dark matter halo surrounding the Milky Way extends approximately 600,000 light-years from the galactic center. Light takes 600,000 years to cross this distance. The halo contains approximately 1 trillion solar masses of dark matter. Every star in our galaxy, including the Sun, orbits within this halo, held in place by its gravity. The halo is what prevents the galaxy from flying apart as it rotates. It's what maintains the orbital stability that allows planetary systems to exist for billions of years without disruption. But the Milky Way's halo is just one node in a much larger structure. Our galaxy is part of the Local Group, a collection of approximately 80 galaxies bound together by their collective dark matter. The Local Group is part of the Virgo supercluster, a larger structure containing approximately 100 galaxy groups and clusters, spanning approximately 110 million light-years. The Virgo supercluster is part of Laniakea, an even larger structure containing approximately 100,000 galaxies, spanning approximately 520 million light-years. And Laniakea is just one of countless superclusters in the observable universe, all connected by the cosmic web of dark matter filaments. You are part of this structure, not metaphorically, literally. The atoms in your body are moving through space as part of the Milky Way's rotation around the galactic center. The Milky Way is moving through space as part of the Local Group's gravitational dynamics. The Local Group is moving through space, falling toward the Virgo cluster under the influence of its dark matter. All of this motion is orchestrated by dark matter's gravity, by the invisible scaffolding that connects everything in the universe. And this motion has consequences. The Local Group is moving through space at approximately 630 kilometers per second relative to the cosmic microwave background, the closest thing we have to an absolute reference frame. This motion creates a dipole pattern in the CMB. The radiation appears slightly hotter in the direction we're moving toward and slightly cooler in the direction we're moving away from. This dipole has been measured with extraordinary precision. It tells us that we're not at rest in the universe. We're falling through space, pulled by the gravity of distant structures made primarily of dark matter. Where are we falling toward? The Great Attractor, a gravitational anomaly located approximately 250 million light-years away in the direction of the constellation Centaurus. The Great Attractor is pulling our Local Group, along with thousands of other galaxies, toward itself at hundreds of kilometers per second. But the Great Attractor itself is being pulled by an even larger structure, the Shapley supercluster, the most massive concentration of galaxies in the nearby universe, located approximately 650 million light-years away. The Shapley supercluster contains more than 8,000 galaxies and has a total mass of approximately 10 to the power of 17 solar masses, 10 million trillion times the mass of the Sun. Most of that mass is dark matter. This is the cosmic web in action. Galaxies aren't distributed randomly. They're organized into a hierarchy of structures, each level shaped by dark matter's gravity. Small galaxies orbit within groups. Groups fall into clusters. Clusters are connected by filaments. Filaments define the boundaries of voids. And all of it, every structure at every scale, is held together by dark matter, the invisible scaffolding that makes cosmic structure possible. The universe is not a collection of isolated objects. It's a connected system, a web of gravitational relationships extending across billions of light-years. And you are part of this web. The dark matter halo surrounding the Milky Way connects you to the Local Group. The Local Group connects you to the Virgo supercluster. The Virgo supercluster connects you to Laniakea. Laniakea connects you to the cosmic web that spans the observable universe. Through dark matter's gravity, you are connected to everything that exists. This connection is not abstract, it's physical. The gravitational influence of distant structures affects the motion of our galaxy, which affects the motion of the solar system, which affects the motion of Earth. The tides that shape our oceans are caused primarily by the moon's gravity, but they're also influenced, infinitesimally, by the gravity of every other object in the universe. The sun's gravity dominates the solar system, but the collective gravity of the Milky Way's dark matter halo determines the sun's orbit around the galactic center. The Milky Way's motion is determined by the gravity of the local group, which is determined by the gravity of larger structures, which is determined by the distribution of dark matter across cosmic scales. Everything is connected. Everything influences everything else. And dark matter is the medium through which these influences propagate, the invisible fabric that binds the universe together. Let me tell you something that will change how you see yourself. You are not made of the universe's primary substance. The atoms in your body, the carbon, oxygen, nitrogen, hydrogen that form your cells, your DNA, your thoughts, represent a cosmic minority. You are built from the exception, not the rule. The universe's dominant form of matter passes through you right now, utterly indifferent to your existence, and yet without it, you would never have existed at all. This is not a metaphor. This is not philosophical speculation. This is the conclusion forced upon us by every observation, every measurement, every simulation of cosmic evolution. We live in a universe where 85% of all matter is fundamentally different from us, invisible, intangible, interacting only through gravity. And this invisible majority is not passive. It's not merely filling space. It's actively shaping reality at every scale, from the formation of galaxies to the stability of your solar system to the very fact that complex chemistry became possible. But here's what makes this truly extraordinary. We discovered this invisible universe not by detecting it directly, but by noticing what it does. We mapped the invisible by observing the visible. We deduced the existence of dark matter through pure reasoning, through the careful application of physical laws to astronomical observations, through the recognition that something was missing from our equations. This is science at its most powerful, revealing truths about reality that lie beyond the reach of our senses. Now, I understand perfectly what you might be thinking. This sounds like pseudoscience. It sounds like we're inventing invisible substances to explain things we don't understand, like medieval philosophers inventing epicycles to explain planetary motion, or 19th century physicists inventing the luminiferous ether to explain how light propagates. History is full of invisible substances that turned out not to exist. Why should dark matter be any different? This is a legitimate question. It deserves a serious answer. And the answer lies in the nature of the evidence and the rigor of the scientific process. When Fritz Zwicky first proposed dark matter in 1933, he was indeed proposing an invisible substance to explain an anomaly. Galaxies in the Coma cluster moving too fast to be held together by visible matter alone. At that point, dark matter was a hypothesis, one possible explanation among several. Zwicky could have been wrong. The measurements could have been flawed. The theory of gravity could have needed modification. Dark matter was not yet established science. But then, Vera Rubin measured galaxy rotation curves in the 1970s and found the same problem. Stars moving too fast to be held together by visible matter. Different observation, different technique, same conclusion. The evidence was accumulating. Then came gravitational lensing observations, showing that light bends around galaxy clusters in ways that require far more mass than we can see. Different observation again, different physical principle, same conclusion. Then came the cosmic microwave background measurements, showing density fluctuations that could only have grown into galaxies if dark matter provided additional gravitational pull in the early universe. Different observation. Different epoch of cosmic history, same conclusion. Then came computer simulations of structure formation, showing that the observed cosmic web, the distribution of galaxies across billions of light-years, matches predictions only if dark matter exists. Different approach, different methodology, same conclusion. Then came observations of colliding galaxy clusters like the Bullet cluster, showing direct separation between the gravitational mass and the visible matter. Different observation, Different physical process, same conclusion. Every independent line of evidence points to the same reality. The universe contains far more matter than we can see, and this matter interacts primarily through gravity. This is not like epicycles or ether. Those were ad hoc additions to theories that were fundamentally flawed. Dark matter is the simplest explanation that accounts for multiple, independent observations across different scales and different epochs of cosmic history. Could we be wrong? Of course. Science is always provisional, always open to revision in light of new evidence. Perhaps dark matter doesn't exist, and instead, our understanding of gravity needs modification. This possibility is taken seriously. Physicists have developed alternative theories, modified Newtonian dynamics, or MOND, and its relativistic extensions, that attempt to explain observations without invoking dark matter. These theories are tested rigorously against observations, and they fail. Not completely. MOND can explain galaxy rotation curves reasonably well, but it fails to explain galaxy cluster dynamics. It fails to explain gravitational lensing observations. It fails to explain the cosmic microwave background. It fails to explain the bullet cluster. It fails to explain the large-scale structure of the universe. To account for all observations, modified gravity theories end up requiring invisible matter anyway. They just call it something else. The evidence for dark matter is overwhelming, not because of any single observation, but because of the convergence of multiple independent lines of evidence. This is how science establishes truth, not through single experiments, but through the accumulation of evidence from different sources, all pointing to the same conclusion. Dark matter has passed this test. It's as well established as any component of modern cosmology. But, and this is crucial, we still don't know what dark matter is. We know it exists. We know how much of it there is. We know how it's distributed. We know what role it plays in cosmic evolution. But we don't know what particles comprise it. We don't know what fundamental physics governs its behavior beyond gravity. We have candidates, WIMPs, axions, sterile neutrinos, primordial black holes, but no confirmed detection. This is not a failure of science. This is science working exactly as it should. We've discovered something real through its effects, and now we're working to understand its nature. This process takes time. It requires patience, ingenuity, and the willingness to accept that some questions don't have immediate answers. The search for dark matter particles continues in laboratories around the world, deep underground, shielded from cosmic rays. Detectors of extraordinary sensitivity wait in silence, hoping to catch the faint whisper of a dark matter particle colliding with an atomic nucleus. Years pass, decades pass, no definitive signal emerges. The detectors become more sensitive. The search continues. This might seem frustrating. We know dark matter exists, the gravitational evidence is overwhelming, yet we cannot capture it, cannot isolate it, cannot examine it directly. But consider what this tells us about the universe. It tells us that reality is stranger than we imagined. It tells us that the matter we're made of, the matter that interacts electromagnetically, that forms atoms and molecules and complex chemistry, is not the universe's default state. It's the exception. The rule is matter that interacts only through gravity, matter that remains forever invisible to electromagnetic radiation, matter that we can know only through its gravitational influence. This should be humbling. We are not made of the universe's primary substance. We are made of a rare form of matter that happens to interact in ways that allow complexity, chemistry, life, consciousness. But we are embedded in an ocean of dark matter, surrounded by it, dependent on it, shaped by it. The visible universe, everything we can see with telescopes, everything that emits or absorbs light, is a thin film of exceptional matter floating in a vast sea of dark matter. And this sea is not uniform. It's structured, dynamic, constantly evolving. The dark matter halo surrounding the Milky Way is not a static sphere. It's filled with streams and clumps, the remnants of smaller halos that merge together over billions of years. Some of these substructures are passing through the galactic disk right now, invisible rivers of dark matter flowing through the space between stars. Their gravitational influence is subtle but real, detectable through careful measurements of stellar motions. The Gaia satellite has revealed some of these structures indirectly by measuring perturbations in stellar streams, those ribbons of stars torn from disrupted dwarf galaxies. When a dark matter clump passes near a stellar stream, it creates a small gravitational tug, a tiny deviation in the stream's trajectory. By mapping these deviations, astronomers are beginning to chart the invisible landscape of dark matter substructure within our galaxy. Each detection is a glimpse of the hidden architecture that surrounds us. But the most profound realization is this: dark matter is not just around us. It's part of our history. Every atom in your body has a story that involves dark matter. The calcium in your bones was forged in a massive star that formed within a dark matter halo. That star lived for millions of years, held in orbit around its galaxy's center by dark matter's gravity. When it exploded as a supernova, scattering calcium and other heavy elements across space, those elements were guided by dark matter's gravitational field into new clouds of gas. Those clouds collapsed to form new stars, including the Sun. The Sun formed within a dark matter halo. Earth formed from material that had been shepherded by dark matter for billions of years. You are not separate from this process. You are the product of it. Every breath you take involves oxygen atoms that were created in stars held together by dark matter. Every heartbeat is powered by chemical reactions involving elements synthesized in stellar cores that ignited because dark matter allowed gas clouds to collapse. Every thought you think involves electrical signals propagating through neurons built from molecules assembled from atoms that exist because dark matter made the universe capable of creating structure. The connection is not abstract. It's physical, causal, direct. Without dark matter, the density fluctuations in the early universe would have been too small to grow. Gravity would have been too weak. The universe would have expanded as a nearly uniform fog of hydrogen and helium, growing thinner and colder forever. No galaxies would have formed, no stars would have ignited, no heavy elements would have been synthesized, no planets would have coalesced, no chemistry would have become complex enough to produce life. The universe would be dark, empty, sterile, incapable of producing anything as complex as a single living cell, let alone a conscious being capable of wondering about its origins. Dark matter made complexity possible. It provided the gravitational scaffolding that allowed structure to form. It created the conditions necessary for stars to ignite, for planets to form, for chemistry to become interesting, for life to emerge, for consciousness to arise. You owe your existence to an invisible substance that you will never see, never touch, never detect directly. You are the product of dark matter's gravitational influence, shaped by forces that operate on scales vastly larger than your body, your planet, your solar system. And this influence continues. Right now, the Sun is orbiting the galactic center at 220 kilometers per second. Held in place primarily by the gravity of the Milky Way's dark matter halo. This orbital motion has been stable for billions of years, allowing Earth to exist in a relatively safe region of the galaxy, far from the chaotic environment near the galactic center, protected from frequent supernova explosions and gamma-ray bursts. This stability is not guaranteed by the visible matter alone. It's maintained by dark matter's gravity, by the invisible halo that keeps the galaxy's structure intact. In approximately 4 billion years, the Milky Way will collide with Andromeda. The two galaxies will merge, their dark matter halos interpenetrating, their stars and gas clouds interacting, their supermassive black holes eventually spiraling together. This merger is inevitable, written into the trajectories of the two galaxies by the distribution of dark matter in the local group. The collision will reshape both galaxies, creating a new elliptical galaxy with a dark matter halo containing approximately 2 trillion solar masses. 2 trillion times the mass of the Sun, all in the form of invisible particles. The solar system will likely survive this collision intact. The distances between stars are so vast that direct collisions are extremely unlikely. But the Sun's orbit will change dramatically. We might be flung into the outer regions of the new galaxy or pulled closer to the center. The night sky will be transformed. The merger will trigger bursts of star formation as gas clouds collide and compress. New stars will ignite, new planetary systems will form, and all of this will be orchestrated by dark matter, by the invisible scaffolding that holds galaxies together and guides their evolution. This is happening throughout the universe. Right now, galaxies are merging, guided by dark matter's gravity. New structures are forming. The cosmic web is evolving. And all of it depends on the invisible majority, the dark matter that dominates the universe's mass, that shapes cosmic structure, that makes complexity possible. Consider the scale of dark matter's influence. The observable universe contains approximately 2 trillion galaxies. Each galaxy is embedded in a dark matter halo. Each halo contains several times more mass than all the visible stars combined. The total mass of dark matter in the observable universe is approximately 6 × 10⁻53 kilograms. 600 quintillion kilograms. This is not a small correction to our understanding of the cosmos. This is the dominant component of reality, the substance that outweighs everything we can see by a factor of more than 5 to 1. And yet, despite its dominance, dark matter remains profoundly mysterious. We can map its distribution across the universe. We can measure its gravitational effects with extraordinary precision. We can simulate how it behaves over billions of years of cosmic evolution. But we cannot capture it. We cannot isolate it. We cannot examine it in a laboratory. It passes through our detectors, through our bodies, through the Earth, utterly indifferent to the normal matter it encounters. This is the paradox of dark matter. It's the most abundant form of matter in the universe, yet we cannot see it. It's the foundation of all cosmic structure, yet we don't know what it's made of. It's shaped our existence, yet it remains fundamentally alien, interacting with our world only through the weakest of forces. But perhaps this is appropriate. Perhaps the universe is teaching us something profound about the limits of human perception and the nature of reality itself. We evolved to perceive electromagnetic radiation, light, because that's what was useful for survival on Earth's surface. Our eyes detect photons. Our instruments detect photons. Our entire understanding of the cosmos is built on observations of light and other forms of electromagnetic radiation. But the universe is not obligated to be visible. The universe is not required to interact with us in ways we find convenient. Most of the matter in the cosmos doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. It's invisible not because it's hiding, but because it simply doesn't participate in the electromagnetic interactions that make things visible. It exists in a different mode, responding only to gravity, forever beyond the reach of our electromagnetic senses. This means that our view of the universe is fundamentally incomplete. We see only the tip of the iceberg, the small fraction of matter that happens to interact electromagnetically. The bulk of reality is hidden from us, detectable only through its gravitational influence. We are like observers who can only hear, trying to understand a world that is primarily visual. We can infer the existence of visual phenomena through their effects on sound, but we cannot experience them directly. We are blind to the universe's dominant component. And yet, we continue to investigate. We build more sensitive detectors. We develop new theories. We run more sophisticated simulations. We refuse to accept ignorance as final. This is what makes us human, not our atoms, which are common throughout the universe, but our curiosity, our drive to understand, our insistence on pushing the boundaries of knowledge even when the answers seem impossibly distant. Dark matter is one of the great mysteries of our time. It's a reminder that the universe is stranger and more complex than we imagined, that reality extends far beyond what our senses can detect, that the visible is not the whole story. We live in a cosmos where the invisible outweighs the visible, where the unknown dwarfs the known, where the majority of matter is fundamentally different from the matter we're made of. But we are not separate from this invisible majority. We are connected to it through gravity, through cosmic history, through the very fact of our existence. Dark matter made galaxies possible. Galaxies made stars possible. Stars made heavy elements possible. Heavy elements made planets possible. Planets made life possible. Life made consciousness possible. And consciousness made it possible for the universe to know itself, to ask questions about its own nature, to discover the invisible forces that shaped its evolution. You are part of this story. You are the universe investigating itself. You are dark matter's way of knowing that it exists. The atoms in your body were assembled through processes that depended entirely on dark matter's gravitational scaffolding. You exist because dark matter exists. You are connected, through billions of years of cosmic evolution, to the invisible architecture that holds the universe together. And right now, as you read these words, dark matter is passing through you. 200 trillion particles every second, streaming through your body at hundreds of kilometers per second, utterly indifferent to your existence. They don't collide with your atoms. They don't interact with your cells. They simply pass through, as they've been passing through everything for billions of years, as they will continue to pass through everything for billions of years to come. But their indifference doesn't diminish their importance. These invisible particles are the reason you exist. They are the scaffolding upon which reality is built. They are the hidden force that holds galaxies together, that guides cosmic evolution, that makes complexity possible. They are the invisible majority, the dark matter that dominates the universe, the substance that shaped everything you see and everything you are. This is the reality we inhabit. This is the universe we're part of. Not a universe of isolated objects, but a connected system where everything influences everything else, where the invisible shapes the visible, where the majority of matter is fundamentally different from us, yet essential to our existence. We are embedded in dark matter's gravitational web, dependent on it, shaped by it, connected through it to every structure in the cosmos. And the most remarkable thing is that we discovered this. We, who are made of the minority form of matter, who can only perceive electromagnetic radiation, who evolved on a small planet orbiting an ordinary star in an unremarkable galaxy. We figured out that the universe is dominated by something we cannot see. We mapped the invisible through pure reasoning. We deduced the existence of dark matter from its gravitational effects. We understood our place in a cosmos where we are the exception, not the rule. This is the power of science. This is what human curiosity can achieve. We are not content to accept the world as it appears. We ask questions. We make measurements. We build theories. We test predictions. We follow the evidence wherever it leads, even when it leads to conclusions that challenge our intuitions, that reveal realities beyond our direct perception, that show us a universe stranger and more wonderful than we imagined. Dark matter is that kind of discovery. It's a revelation about the true nature of the cosmos, about the invisible forces that shape reality, about our place in a universe where the visible is the minority and the invisible is the norm. It's a reminder that reality is not limited to what we can see, that the universe is under no obligation to be comprehensible to creatures like us, and yet, remarkably, miraculously, we can understand it anyway. We can map the invisible. We can deduce the hidden. We can know the unknowable, at least in part. And in doing so, we fulfill our role in the universe's grand narrative. We are the cosmos becoming aware of itself, investigating its own foundations, discovering the invisible architecture that makes existence possible. The dark matter passes through you. You pass through the dark matter. And in that mutual interpenetration, in that cosmic dance of visible and invisible, the universe continues its work of creating structure, building complexity, generating consciousness, and asking questions about its own nature. So here we are. You've traveled with me from the particles streaming through your body right now, back through 13.8 billion years of cosmic history, out to the edges of the observable universe, and back again. You've seen how dark matter shaped everything, from the first galaxies to the calcium in your bones. You understand that you are made of the cosmic minority, living in an ocean of invisible majority. You know that without dark matter, none of this would exist. But now I need to tell you something that might be uncomfortable. we still don't really know what dark matter is. Yes, we know it exists. Yes, we can map it. Yes, we understand its role in cosmic evolution with extraordinary precision. But the fundamental question, what are these particles, remains unanswered. And this isn't just a gap in our knowledge, it's a window into something deeper, something that challenges our understanding of reality itself. Think about what this means. We live in a universe where 85% of all matter is made of something we cannot identify. We've built detectors of extraordinary sensitivity, buried them kilometers underground, waited for years, and found nothing definitive. We've smashed particles together at energies approaching the Big Bang, and dark matter hasn't appeared. We've searched across 20 orders of magnitude of possible particle masses, and the universe has remained silent. This silence is profound. It's telling us that dark matter is even stranger than we thought. If dark matter were made of particles that interact even weakly with normal matter, the WIMPs that many physicists expected, we should have detected them by now. The fact that we haven't means one of several possibilities, and none of them are simple. Perhaps dark matter particles are far lighter than we expected, so light that they cannot create the nuclear recoils our detectors are designed to catch. Perhaps they're far heavier, so massive that they're incredibly rare, and we simply haven't been lucky enough to see one yet. Perhaps they interact through forces we haven't discovered, forces that don't couple to any particles in the standard model. Perhaps dark matter isn't particles at all, but something more exotic. Primordial black holes, or topological defects in spacetime, or something we haven't even imagined yet. Or perhaps, and this is the most unsettling possibility, dark matter is telling us that our understanding of physics is incomplete in ways we don't yet recognize. Maybe there are entire sectors of reality that we cannot access, cannot detect, cannot even conceive of properly because we lack the theoretical framework to understand them. Maybe the universe is far stranger than our current physics allows us to imagine. Consider the possibility of a dark sector, a whole family of dark matter particles with their own forces and interactions, completely separate from the standard model. In this scenario, dark matter wouldn't be a single type of particle, but an entire parallel physics, as rich and complex as our own. There could be dark photons mediating dark electromagnetic forces. There could be dark atoms, bound together by these dark forces. There could be dark chemistry, dark molecules, perhaps even dark complexity we cannot begin to fathom. This isn't science fiction. This is a serious theoretical possibility. The standard model contains one sector of matter, quarks and leptons interacting through electromagnetic, weak, and strong forces. But there's no fundamental principle that says this is the only sector that can exist. The universe could contain multiple sectors, each with its own particles and forces, each invisible to the others except through gravity. We would only be aware of our own sector, the one that interacts electromagnetically and allows the chemistry necessary for life. If this is true, then the universe is far more complex than we've imagined. The visible cosmos, everything we can see, everything we can detect with electromagnetic radiation, would be just one layer of reality. There could be entire structures made of dark matter, held together by dark forces, existing in the same space as our galaxies, but completely invisible to us. Dark matter galaxies, dark matter stars, perhaps even dark matter planets, though without electromagnetic interactions, they would be profoundly different from anything we know. Could there be dark matter life? This seems absurd at first. Life as we know it depends on chemistry, and chemistry depends on electromagnetic interactions between atoms. Dark matter doesn't interact electromagnetically, so how could it form the complex structures necessary for life? But this assumes that life must be like our life, that complexity must arise through our kind of chemistry. If dark matter has its own forces, its own interactions, then perhaps it could form its own kind of complexity, its own kind of structure, its own kind of something. Not life as we know it, but something analogous, something we lack the concepts to properly describe. This is pure speculation, of course. We have no evidence for dark matter complexity beyond gravitational clumping. But the point is this: we don't know. We don't know what dark matter is capable of. We don't know what structures it might form. We don't know what physics governs its behavior beyond gravity. We are profoundly ignorant about the dominant component of the universe. And this ignorance extends beyond dark matter. Consider dark energy, the mysterious force causing the universe's expansion to accelerate. We know even less about dark energy than we do about dark matter. We can measure its effects. We can quantify how much of it there is, approximately 68% of the universe's total energy content. But we have no idea what it is, no idea what causes it, no idea whether it's a property of space itself, or a new field pervading the universe, or something else entirely. Dark matter and dark energy together make up 95% of the universe's total energy content. 95%. Everything we understand, all of particle physics, all of chemistry, all of biology, all of human civilization, is built from the remaining 5%. We are the exception. We are the minority. We are the thin film of complexity floating on an ocean of mystery. This should be humbling. We've made extraordinary progress in understanding the universe. We've mapped cosmic structure across billions of light years. We've traced the history of the cosmos back to fractions of a second after the Big Bang. We've discovered fundamental particles and forces. We've understood how stars work, how galaxies form, how planets evolve. We've even begun to understand the origins of life and consciousness. These are remarkable achievements, but they're achievements in understanding 5% of reality. The other 95% remains mysterious. We know it's there, we can measure its effects, but we don't know what it is. We are like cartographers who have mapped the coastlines of continents but have no idea what lies in the interior. We've charted the visible universe with extraordinary precision, but the invisible universe, the dominant component of reality, remains largely unknown. And there's something else we don't know, something even more fundamental. Why does the universe have the properties it has? Why is dark matter approximately 27% of the total energy content, and dark energy approximately 68%, and normal matter approximately 5%? Why these particular ratios? If dark matter were slightly more abundant, structure would have formed earlier and more efficiently. If it were slightly less abundant, galaxies might not have formed at all. If dark energy were stronger, it would have prevented structure formation entirely. If it were weaker, the universe might have recollapsed long ago. The universe seems to be balanced on a knife edge, with properties precisely tuned to allow structure, complexity, and life to emerge. This is sometimes called the fine-tuning problem, and it's one of the deepest mysteries in cosmology. Is this fine-tuning just a coincidence? Is it a consequence of some deeper physical principle we haven't discovered? Or is our universe just one of countless universes in a vast multiverse, and we happen to exist in one with properties that allow observers to exist? We don't know. We have theories, string theory, eternal inflation, the anthropic principle, but no definitive answers. The universe's fundamental properties remain unexplained. We can measure them with extraordinary precision, but we cannot explain why they have the values they do. There's also the question of what came before the Big Bang. Our current physics breaks down at the moment of the Big Bang itself. We can trace cosmic history back to fractions of a second after the initial moment, but we cannot see beyond that barrier. What caused the Big Bang? What, if anything, existed before it? Was there a before, or does time itself begin with the Big Bang? These questions remain unanswered, perhaps unanswerable with our current understanding of physics. And then there's the ultimate question. Why does anything exist at all? Why is there something rather than nothing? This might seem like a philosophical question rather than a scientific one, but it's deeply connected to physics. The laws of physics describe how things behave, but they don't explain why those laws exist, or why the universe follows laws at all. Why is there a cosmos governed by mathematical principles? Why is reality comprehensible? Why can conscious beings like us understand the universe's workings? These are not questions that science can currently answer. They might be questions that science can never answer. But they're questions worth asking because they remind us of the limits of our knowledge and the vastness of what remains unknown. Now, let me bring you back to where we started. Remember the opening image? 200 trillion dark matter particles passing through your body every second, streaming through you at hundreds of kilometers per second, utterly indifferent to your existence. You now understand what those particles are doing, or rather, what they're not doing. They're not interacting with your atoms. They're not colliding with your cells. They're simply passing through, as they've been passing through everything for billions of years. But you also understand what those particles represent. They represent the invisible majority, the dominant component of the universe, the scaffolding upon which all visible structure is built. They represent a form of matter fundamentally different from the matter you're made of, yet essential to your existence. They represent a mystery that we've discovered but not yet solved, a question that we've learned to ask but cannot yet answer. And here's the profound realization. You are connected to this mystery, not metaphorically, literally. The atoms in your body exist because dark matter made structure formation possible. The calcium in your bones was forged in stars that formed within dark matter halos. The oxygen you breathe was created in stellar cores that ignited because dark matter allowed gas clouds to collapse. Every element heavier than helium in your body, the carbon, the nitrogen, the phosphorus, the iron, was synthesized in stars whose existence depended on dark matter's gravitational scaffolding. You are made of stardust, yes, but those stars were made possible by dark matter. You are, in a very real sense, a product of the invisible universe. Your existence is proof that dark matter exists, that it shaped cosmic evolution, that it made complexity possible. You are the visible consequence of invisible causes, the tangible result of intangible forces, the conscious product of an unconscious cosmos. And you are part of an ongoing story. The universe is still evolving. Dark matter is still shaping cosmic structure. Galaxies are still forming, still merging, still being guided by dark matter's gravity. The Milky Way is still orbiting within its dark matter halo. The solar system is still moving through the galactic disk, bobbing up and down through regions of varying dark matter density. Earth is still orbiting the sun, held in place by gravity, bathed in sunlight, supporting life, generating consciousness. All of this is temporary. In approximately 4 billion years, the Milky Way will merge with Andromeda. In approximately 100 billion years, the accelerating expansion driven by dark energy will have carried distant galaxies beyond the cosmic horizon. In approximately 1 trillion years, the last stars will burn out, and the universe will enter an era of darkness. In approximately 10 to the power of 100 years, even black holes will evaporate through Hawking radiation, and the universe will be nothing but a thin soup of particles, growing colder and more diffuse forever. But right now, in this brief cosmic moment, structure exists. Complexity exists. Life exists. Consciousness exists. You exist. And you have the extraordinary privilege of being able to understand, at least partially, how you came to be. You can trace your origins back through billions of years of cosmic evolution, back through generations of stars, back through the formation of galaxies, back through the collapse of dark matter halos, back through the density fluctuations in the early universe, back to the first moments after the Big Bang. You are the universe becoming aware of itself. You are the cosmos investigating its own foundations. You are dark matter's way of knowing that it exists. And in this moment of awareness, in this act of understanding, you fulfill a role that is unique in the cosmos. The role of observer, questioner, seeker of truth. The dark matter doesn't know it exists. It doesn't know it shaped galaxies. It doesn't know it made your existence possible. It simply exists, responding to gravity, clustering into halos, forming the invisible scaffolding of reality. But you know. You, who are made of the minority form of matter, who can only perceive electromagnetic radiation, who evolved on a small planet in an unremarkable galaxy, you know about dark matter. You understand its role. You appreciate its importance. This is the miracle of consciousness. This is the wonder of human curiosity. We are not content to simply exist. We ask why. We ask how. We build telescopes and particle detectors. We develop theories and run simulations. We map the invisible and deduce the hidden. We push the boundaries of knowledge, even when the answers seem impossibly distant, even when we know we might never find them. And perhaps that's the point. Perhaps the search itself is what matters, not the destination. Perhaps the questions are more important than the answers. Perhaps the universe is not meant to be fully understood, but endlessly explored, forever revealing new mysteries as we solve old ones, always keeping us humble, always reminding us that reality is stranger and more wonderful than we can imagine. Dark matter is one of those mysteries. It's a reminder that the visible is not the whole story, that the universe extends far beyond what our senses can detect, that reality is not obligated to be comprehensible to creatures like us. And yet, remarkably, we can comprehend it, at least partially, at least enough to know that it exists, to map its distribution, to understand its role in cosmic evolution. We live in a universe where the invisible outweighs the visible, where the unknown dwarfs the known, where the majority of matter is fundamentally different from us. But we are not separate from this invisible majority. We are connected to it through gravity, through cosmic history, through the very fact of our existence. We are embedded in dark matter's gravitational web, dependent on it, shaped by it, connected through it to every structure in the cosmos. And right now, as you finish reading these words, dark matter continues its work. It holds galaxies together. It guides cosmic evolution. It passes through you, through the Earth, through the Sun, utterly indifferent to the normal matter it encounters. It has been doing this for billions of years. It will continue doing this for billions of years to come. But in this moment, you are aware of it. You understand it. You appreciate it. And in that awareness, in that understanding, in that appreciation, you participate in something profound. The universe's ongoing project of knowing itself, of understanding its own nature, of asking questions about its own existence. The dark matter passes through you. You pass through the dark matter. And in that mutual interpenetration, in that cosmic dance of visible and invisible, the universe continues its work of creating structure, building complexity, generating consciousness, and asking questions that may never be fully answered. Perhaps that's exactly as it should be. Perhaps the mystery is the point. Perhaps the universe is not a puzzle to be solved, but a wonder to be experienced. An endless source of questions that keep us curious, keep us humble, keep us searching. You are part of this search. You are part of this mystery. You are part of this invisible universe that shaped everything you see and everything you are. And that connection, that deep, physical, causal connection between you and the dark matter that dominates the cosmos, is perhaps the most profound realization of all. You are not separate from the universe. You are not an isolated observer looking at reality from the outside. You are part of it, woven into its fabric, your existence dependent on processes that operate on scales from the subatomic to the cosmic. The dark matter that holds galaxies together is the same dark matter that made your existence possible. The invisible architecture that spans the universe is the foundation upon which your life is built. And in this moment of understanding, in this recognition of your place in the cosmic web, you fulfill your role in the universe's grand narrative. You are the cosmos becoming aware of itself. You are dark matter's way of knowing that it exists. You are the visible consequence of invisible causes, the conscious product of an unconscious universe, the question that reality asks about itself. The dark matter passes through you, and you, in turn, pass through the mystery, forever connected to the invisible force that holds everything together, forever part of the cosmic story that began 13.8 billion years ago and continues in this very moment, in your very existence, in your very awareness of the profound strangeness and beauty of the universe you inhabit.